Welcome you all to this course on defects in material. So far we have covered perfect crystals where no defects are present in the material. But we know all natural material, when we look at it, they do contain some type of the defect or the other. We will talk about the various types of defects in the course of this lecture. The question which arises is that why do defects form at all in the material? That is one. And another is all the defects bring down the free energy of the system, or is it that some of the defects increase the free energy of the system? This situation can also arise, right? Some could be artificially created in the material, some may be that naturally they will have. Okay. In this one type of a defect which actually brings down the free energy of the system, which we will be talking about, is the vacancies. Okay. So, what we will be talking about today, okay, are in a course of 3 or 4 lectures on point defects in materials. Okay. When we talk of point defects, what are the type of point defects which we can have? One, they could be vacancies, interstitials, okay. Then this could be substitutional and interstitial impurity atoms which could be there. They are occupying isolated atom positions in the crystal, okay. And the systems could be metallic, covalent bonded, or ionic materials, or ordered alloy. In all these type of materials, point defects could occur. Okay. Then the next question is that whether these point defects are energetically, okay, they bring down the free energy of the system. We have to look at it from the energy point of view. Okay. That depending upon that, we will tell whether they are equilibrium defects or non-equilibrium defects. Correct. Then what is the structure of this defect? That is, if a defect has been created, some to bring down the strain energy, some of the atoms may be, or to maintain the charge balance, atoms may be moving little bit forward or backward. That will give rise to some distortion around the lattice site. Okay. That is what it will bring up, decide what is going to be the structure of the defect. Okay. Then what we have to know about the defect is that how much defects are present, okay. What is the equilibrium concentration of the defect which we can have. Then how to identify these various defects, what are the techniques which are available. Not only identifying the defects, if we have to use it usefully in many of the design considerations of materials, okay, we should also be able to quantify how much the defects are present, correct. Okay. And towards the end, possibly I will be talking about these defects influence property of the material. A brief information I will talk about it. But what is essentially important is that of all these defects, vacancy is the one which is the most important defect, because the vacancy is the one which controls the entire phase transformation which are taking place in the material, and how the property of the material changes during service as well as during aging, correct. That is what is very important. So, that is why the study of vacancy generation in the material and how the kinetics of vacancy movement is very important. Okay. Before we go into these details, let us just look at the different types of vacancies which are produced in materials. Let us take the case of a pure metals, okay, where the type of vacancy which we can produce. If you take a perfect crystal, in this one all atoms are occupying regular lattice positions, correct. All the lattice positions they are occupying. If, for example, I remove an atom from this particular site, okay, then it will generate a vacancy, okay. And here that black line shows the lattice lines. So, the absence of atom, immediately one can see that when an atom has been removed, the force balance between the atoms are keeping the atoms at particular positions. Now you can see that immediately the atoms which are at this lattice point that has moved closer, the adjacent atoms, these atoms also move close. So there is a distortion which is created around each of the lattice positions, correct? That is close to it. This is what we are considering, it is only a two-dimensional simple cubic lattice, okay, square lattice. Now let us look at, these are about vacancies. Suppose we are trying to insert an atom of the same material, where can it go? Okay. So all atom positions on the lattice sites are occupied, then it has to go to a position which is an interstices which is remaining in the crystal, which is there in the crystal. The type of interstices which could be there in different type of crystals, that has been covered in the crystallography class. Okay. So in this particular case, when we consider the atom can occupy this center of this lattice or the unit cell, correct? Randomly it can occupy it. When it comes to that center, what is essentially is happening? Okay, all other adjacent atoms, okay, this will be shifted away from their equilibrium positions, little bit away, because lot of strains are being introduced into that region locally. So this, not only the strain, okay, we are bringing atoms which are at equilibrium distance, now put on another atom which is close by. So the repulsive forces between the atoms also will increase, that will also be responsible for movement of atoms away from each other. Okay. That is how the distortion or the strain is generated around the defect position, okay, locally. Now let us consider the case where the case which we have considered just now when I talked about is about an atom which is the same type of an atom which is introduced. There are many cases where we have seen that interstitials, many atoms which have like light elements like carbon, oxygen, nitrogen have small size, they can also be introduced into the lattice. So they would like to prefer to come into some interstitious position. Okay. When they occupy the interstitious position, we should understand that even they may create a small distortion around it, because that distortion is because depending upon the type of interaction which it has with the neighboring atoms. Okay. There could be a repulsive force which may be moving the atom away, okay. But the extent to which atoms are moved from the lattice sites, okay, repelled, may be less. Okay. So this is essentially an impurity atom, and this impurity atom is always externally added. Okay. In the earlier case, I had not mentioned how this atom is coming into this lattice site, which we will talk about it later. Okay. Let us consider the case of a impurity which is added, which is to a substitutional site. Okay. If we add an impurity to a substitutional site, okay, that impurity could be either a larger than the atoms, neighboring atoms, or it could be smaller than that. In these cases also, they will be introducing distortions locally around the lattice site. Okay. That is what leads to strengthening of the material, hardening of the material. Okay. Here one should be understand that when a substitutional impurity is added, the position which it can occupy in the lattice is already fixed. It can replace only an atom position. When an interstitial position an atom is occupying, once in a lattice one particular position is occupied by a particular type of an atom, all other special positions which are there, which are shown in the Wyckoff table, all are potential positions where the interstitials can go and occupy. So for the interstitial, the number of positions which are available are very large, and the energetics decide which position it will occupy, the lattice. Okay. The substitutional impurity could be smaller also, either case there could be a distortion which will be generated around the lattice point. Okay. But there is another type of a defect which can be produced because so far we talked about vacancies and interstitials, right. There are cases where both vacancy and interstitial could be produced simultaneously in the sample. Okay. This happens during irradiation of a material with high energy ions, where what happens is that atoms are knocked out from the lattice sites. Okay. So a vacancy is created. This knocked out atom comes and occupies some position. It can only occupy an interstitial position. Okay. So these type of defects are called as the Frenkel defects, where we have an interstitial as well as a vacancy type of defect is present simultaneously. Okay. Now, so far we considered this could, whatever we have discussed so far is true for metallic systems, or it is also true for a system which is a disordered alloy. When I say that it is a disordered alloy, what I mean that the position which the atoms can occupy in the lattice, okay, is not fixed, because otherwise we know that the special positions which are there, if one atom is occupying a particular position, in an ordered alloy another atom will occupy only as another specific position, Wyckoff position in the lattice. Okay. In a disordered alloy, what happens is that, especially in substitutional impurities, when an element has been added, this element has replaced some of the atom positions, but which position it is going to occupy will be essentially is random. Okay. But when we say disordered, it does not mean that the alloy is positionally disordered, it is compositionally disordered. Okay. That one should keep it in mind. Okay. When this sort of that is what this grey color or the color of the earth, which I am showing it for the atom to show that it is a disordered. So what will be the probability of an atom occupying a position, particular position? That probability corresponds to, okay, the average composition or the concentration of the element which is present. Okay. Now I am showing another case. This is also a perfect lattice. There is no defects we have considered. Now let us look at another case, okay, where the same lattice, but now atoms occupy specific positions in the lattice sites. Okay. Here if we look at it, the A atom occupies this alpha site, B atom, the pink colored ones, occupy the beta sites. Okay. These sites they are occupying in a regular periodic arrangement. Okay. Now all A atoms are occupying A site and B atoms are occupying only B sites. In such a case, okay, what will be the order parameter, or what is going to be the order in this case? It is a perfectly ordered alloy. Okay. We will come to it later shortly, because we define an order parameter also in this case. But even in this perfectly ordered alloy, there are certain types of defects which could be produced. It is not vacancies or interstitials. Okay. You just now look at this third case which I am showing it. Here, this is a alpha site where instead of an A atom occupying, a B atom is occupying this position, and here it is a beta site where instead of a B atom, A atom is occupying the position. Otherwise, all the lattice sites are occupied. Okay. But if you look at the number of sites A atom is occupying and number of sites the B atom is occupying, it is not 100%, there is a less, one less here. So when it is less, the order parameter is defined in terms of the number of sites the lattices are occupying. Okay. How exactly an order parameter is defined? Here Nd is, if this alloy having this specific composition is disordered, then number of sites either A atom or a B atom will occupy is given by this value Nd. Okay? Np decides when there is a perfect order how many A atom sites are occupied, how many B atom sites are occupied. And this NO decides in the ordered alloy, okay, how many A atom sites or B atom sites are actually occupied. Okay. If it is perfectly ordered, then this NO will be equal to NP, correct? So this ratio will turn out to be 1. Then when the ratio is 1, we call it as a perfectly ordered alloy, right? Like the case which is being shown in this middle one. Here if you, not the middle one, the last case, here you find that not all the atoms are occupying that site, one atom is less, right? But the perfect order position is NP, and here the number which is occupying it is less. In the disordered case, if you see that this value will be, this difference will be less than the denominator, correct? So then the order parameter will be less. Yes?
The defects, are these the majority defects, or we will find only anti-side defects when it is an ordered alloy, or?
No, other defects will come. No, just I am talking about it that the first type of a defect, even if point defects, the type of point defect can be generated even in a perfectly ordered alloy. Ideal case, alloy also, this type of defects can occur.
So the
Vacancies will come.
will also
Yeah, okay, that I am coming to it later. First I wanted to understand that this is the type of defect which can form, because ordered alloys are the ones which quite often we deal with in metallurgy, okay. But in ordered cases compared to disordered cases or compared to ionic cases, there are types of defects which are being present. Before introducing it, even in a perfectly ordered, where there are no point defects are generated, even then we can have a disorder in the material. Some defect could be there. These defects are the anti-side defects. That is what I am trying to explain. Okay. So here, suppose this value N0, the number of positions in the perfect lattice it is occupying, corresponds to that of the disordered number of atoms. Then this will turn out to be 0. This will be some factors which remains constant. So order parameter will become 0. So order parameter, this is how it is being defined, and this is what we call it as a long range order parameter. Okay. This clear? How the long range order parameter is defined? Okay. So these defects are called as anti-side defects. Okay. Still we are now dealing with an ideal crystal only, ordered crystal which we have considered. Now let us consider a system, ordered system, where defects are introduced into the lattice. Okay. So let us consider the case where on the A side, okay, we have a vacancy which has been created. That is, one of the A atom is missing from that alpha side. Okay. Okay. That I had just put it as an A atom which is missing there. Okay. What are the possibilities now if a vacancy has to move? Which are the type of atoms which can jump into this site? One possibility is that this B atom is closest to it, it can jump to this site, correct? Or the A atom which is slightly far away, that can also jump to that site. These are all the two possibilities are there, so that the defect moves, right? For diffusion to occur, the defect has to move. So these two possibilities exist. Then, which is the one which will take place? Okay. Similarly, we can look here. This is a B atom site, okay, in which also similar process can take place. Either an A atom can jump to that site, or a B atom can jump to that beta site. Okay. Both the possibilities are there. you think of the case what will happen if to an A site, alpha site, B atom jumps. What are changes which can happen to this sample? Then the order will get reduced. That means that there is going to increase the energy of the system, correct? So essentially, if an A atom jumps to an A site, alpha site, okay, where a vacancy is created, then the order parameter does not change. Okay, it is only the vacancy is moving around, so no change in energy. If a B atom jumps to that site, order parameter is going to change. That means the change of energy is there. That is not the one which is preferred. Okay. So what will essentially will happen is that because of this reason, now even though an adjacent atom is there which is of a different type, it would not like to jump into that site, correct? So vacancy diffusion, if you look at it in an ordered alloy, is going to be different from that which we see in a disordered alloy. Okay? That means that an atom which is further away will be jumping into that site because it is the same type of an atom. So each of the atoms can have a different type of mobility associated with it. So they may be moving with different rates. All these things could occur. Okay? Because of that, what is essentially is going to happen is that diffusion rates could get reduced compared to that of disordered material. What is the consequence of it in terms of choosing a material, especially for creep behavior if you try to look at it? We would like to have a material when it is ordered, okay? We say that diffusivity comes down. This is the reason why diffusivity comes down in an ordered material and the creep rate will be lower. Is it clear? So this is a type of a defect which is seen only in ordered materials. Okay, in a disordered material we do not see this type of defect, anti-Seitz's defect. Okay. This is just an example where I have taken where we can have an A type of a defect as well as a B type of a defect. Okay. Both are possible in the lattice. Now let us consider the case. So far we have considered pure metallic or disordered systems, alloy systems. Now we have considered a case where it is a perfectly ordered alloy. Now let us consider the case where it is not a metallic type of a bonding, it is an ionic or covalent type of a bonding. Let us take the example of an ionic bonding. Okay. What I have considered here is I am just showing the defect which are the lattice of sodium chloride, which is an ionic bonded crystal. Okay. It is two FCC type of lattices, okay, occupied by either one sodium and another by chlorine, which are interpenetrating each other. Okay. Still it generates the FCC type of an ordered lattice. Okay. As a two-dimensional lattice, I am just showing only one of the phases. You consider that it is an 100 phase which I am showing it. Okay. Here the positive ions or the cations are shown with the red one, not red, pink color, and the green color shows the chlorine ions. Okay. And what is essentially important in a ionic or covalent bonded material is that the charge neutrality always has to be maintained whenever defects are produced in the lattice. Whereas in metallic systems, you are not looking at the charge neutrality. Okay. Here that is very much important. Okay. So then what will happen when we look for the charge neutrality? Okay. So if we produce a vacancy in this particular site where that anion is missing, then there should be some other in the lattice. We should create a vacancy of a cation also, so that the charge neutrality is being maintained. Okay. So to maintain charge neutrality in a when point defects are produced, both cations and anions have to be produced in equal concentration in the material. Okay. These type of defects are called as Schottky defects. Okay? Yes?
These defects, for example, what happens to these atoms? Where do they go? Missing atoms.
Which one? Okay, I will come to that a little bit later, how these defects could be produced in the lattice. The next one, which once it is completed about the type of defects in material, I will be talking about that aspect of it. Okay? These are all the. Now let us look at, now we have considered the Schottky defect. Is there any other way in which a defect could be produced? Okay. The way in which it can produced in ionic bonded material, the one way in which it could happen is that a cation has been removed from this site and it is deposited in a region which is adjacent to it into an interstitial position. Okay. Then also charge neutrality is being maintained. Okay. This type of defects we call it as the Frenkel defects. This is the only type of a defect which we see in disordered materials when we do irradiation, those conditions, correct? Whereas Schottky defects are seen only in directionally bonded materials. Okay. Okay. Now, so far we have considered the defects which are essentially by removing an atom from a particular lattice site, whether it is a cation or an anion. As I mentioned earlier, most of the materials are imperfect. Okay. We can have impurity atoms into that material. So it could be, this impurity can have a charge state which is different from that of the charge state of the other ions which are present in the sample. Okay, let us take the case where it is essentially the anion has got a charge which is not singly ionized, it is doubly ionized. Okay. If it occupies a position like this in this lattice, okay, to compensate for the one negative charge which has come into this site, one excess positive charge has to be added. Okay. If the lattice is otherwise perfect, perfect lattice, then only place which it can come to is some interstitial site, it is very close by. If it goes very far away, then it will be locally creating a field. Okay. So generally they would try to prefer to form as close as possible to where the defect is present. Okay. About these aspects we will talk about it much later. Okay. Some consequences of this. And another possibility, okay, this is what I am showing, it is how these defects will be produced. The other possibility is that we have this particular position, okay, where we have a cation, okay, divalent cation has been introduced. Okay. If a divalent cation has been introduced, okay, to compensate for the negative charge, I can introduce one more negative charge, like in this case where it is an interstitial position, or what I can do it is, because one positive charge is in excess, so I remove from one lattice site one of the ion, then also the charge will be compensated. So this way I can create, the charge neutrality could be maintained. These two possibilities exist, way in which charge neutrality can be maintained in that system. But if I have to introduce one cation, then not cation, anion into an interstitial site, the energy which is required is going to be high. So generally in most of the systems it is essentially creation of an vacancy which is been seen. So these vacancies are not the ones which are generated because of the charge neutrality. The charge neutrality is the reason, but this is because of the type of impurity which we have added. If we add a divalent impurity, the concentration of that impurity will decide how much is going to be the vacancy, that is cation vacancy concentration which we are going to introduce into the lattice. You understand that? This is apart from thermodynamically dictated Schottky defects which will be produced in the lattice. This is going to be the case in most of the materials, because no material is perfectly pure, correct? Some impurities are always there in the material. Okay. Now let us look at the mechanism of a creation of a vacancy. Okay. How can a vacancy be created in a lattice? We consider a crystal without a defect. Okay, it's a perfect ideal crystal. How can we create a vacancy in this crystal? What's the possibility? An atom has to be removed. What is the way in which it can happen? Is that at any particular temperature when we consider it, atoms are vibrating around the lattice points. Okay. It can so happen that not only that the vibrational energy which each of the sites, though we talk about average energy, some sites could have got energy which is higher than that of the others. It can so happen that one of the atom is knocked out from a site. Okay. That is, an atom from this site has just moved out of it and come to this surface. So here one vacancy has been created on the surface. Okay. Suppose an atom from here now moves to the surface, then what will happen? This vacancy will become the one which is generated in the bulk. That is the next case which we have considered here, correct? Now, again this process can take place because now an atom from this site has moved here. Okay, like this with few movements you find that the vacancy has, now the vacancy is within the sample, but an atom has been removed and that is put onto the surface. This is the mechanism by which, no, to answer your question, this is how vacancies are created in the system. Okay, because this is coming essentially because of the thermal vibrations which are associated with it. And though we talk about all atom positions, is any particular atom sitting on any particular lattice at high temperatures? No. They are all moving around continuously because of diffusion. On the average, we will say that this is the way the atoms are distributed. But if we look at one particular atom to find out whether it is sitting at a specific particular position, can we fix the coordinates? No, it just moves around. Yes.
So in case of ionic crystals,
Yeah.
the mechanism will be similar?
In the case of ionic crystals also, the same thing has to happen. Okay. But there the defect concentration which we produce, okay, will be both cation and anion concentration has to be produced, and we have to consider both the sublattices separately, like the way we do for ordered alloys. Okay.
First step of defect formation will be from the surface.
First step of defect formation is from the surface is the one which one can easily think of. This is one way of explaining how the defects are formed, which we can logically understand. It can because otherwise how will be the other way in which we can think of this mechanism itself is that suppose we assume that I remove an atom from by applying some energy, because if you look at in this case there are 4 bonds are there in a 2-dimensional bond, or in a cubic lattice 6 bonds are going to be nearest neighbor bonds. Some energy is required to break this bond, each of this bond. Okay. So how many it will be there? Essentially we are going to have some nearest neighbor bonds. If we can, 6 bonds have to be broken. Okay. This atom is removed from there, and assume that by some means we are bringing it and putting it on the surface. When we put on the surface, it will be again forming some bonds. Okay. What is the difference between the number of bonds? That is going to give you the energy which is required, and there will be some relaxation which will take place. The net effect of all these things is going to decide what is going to be the energy which is required for a vacancies to be created. Okay. But in that, what I described just now, we are not talking about how we are removing it, atom. But logically, if you think of it, the easiest way in which a vacancy could be produced is first creating a vacancy in the surface and that vacancy moving inward by diffusion. Okay. Generally, that is, if I like to break a bond, what has been seen in most of the cases, especially in radiation damage, it has been a lot of calculations have been done. People have seen that it requires around on the average 25 electron volt to 40 electron volts, okay, in most of the material. The value lies in this range to generate a vacancy interstitial pair. Okay. This is the order which is required. But generally when we talk of a formation energy of a vacancy, what we talk about it, it is very small value of the order of maybe around 0.5 eV to 4 eV. Okay. That is because in that case, the whatever is the vacant atom which has been removed, okay, since that comes onto the surface, the net energy difference only what we have to consider as a formation energy. Okay. Because there is some energy loss and there is some energy gain is also going to be there. The net difference is what the energy which is required. Okay. Now the question which comes is that we have to look at these vacancies. What is the concentration of these vacancies? Okay. And whether first this vacancy, because as I mentioned earlier that the various types of defects, whether the defects could be in equilibrium or not. How do we find out whether the defect will be in equilibrium or not? So what are the energy changes which are takes place? Let us take the case of a point defect, a vacancy. We have removed an atom from a lattice site. To remove that atom, some free energy change is going to take place. That much energy has to be spent to remove an atom from that site. The net energy of formation of a vacancy. Then when this vacancy has been created, now if you look at what are sites which this vacancy can occupy in the lattice. In the lattice, it can occupy so many positions which are available. Any one of these positions it could reside. So this is what we call it as a, this gives rise to what is called as a configurational entropy term. So one is a energy which has to be spent. There is a gain in energy which comes from the configurational entropy. The total energy change is a sum of these two, which decides whether there is going to be a change in energy or not. Okay. This is what the philosophy which we use it to calculate. Suppose n vacancies are produced. Okay. Then what will be the, we can find out what is going to be the equilibrium concentration of defects. We can calculate it by taking the what is going to be the free energy change when n vacancies are created. Okay. Then try to differentiate it to find out the minimum free energy which will occur with respect to a number of defects which are going to be there. Okay. That is how theoretically we try to find out the free energy change which will take place, or the same thing can be used to find out the equilibrium concentration of the vacancies which are going to be there in the material. Okay. This is one. And one question which I have added is that one is that question which is, are the vacancies in thermal equilibrium or not? Another question is that can we have a vacancy concentration, okay, which is not in thermal equilibrium? Is it possible to have it? Any situation which you can think of where it can happen? During radiation damage. Any other case you can think of? Eh? By applying stress you can do that. The other is that when we deform a material, when dislocations interact, they produce lot of vacancies. Okay. Or you do mechanical alloying which you do. Lots of defects are introduced into the lattice, that energy into it. But these defects are all non-equilibrium defect concentration. So there are many ways in which we can have defects. But then that question also comes is that when they will come to an equilibrium. This we will talk about it later. But now I just posed this question that there are many situations we can have non-equilibrium concentration of defects as well. Okay. So to find out an answer to whether the defect concentration, what is going to be the defect concentration, okay, how much we can have it, what we are trying to find out is that what is going to be the free energy change when we introduce defects in the lattice. Okay. How do we find out the configurational entropy? The configurational entropy part of it, this W, K is the Boltzmann constant. Okay. W is nothing but the number of combinations are the number of ways in which these vacancies could be arranged in the lattice, correct? That is given by this formula NCN, where capital N is the number of capital N is going to be the total number of atoms, and N is going to be the number of vacant sites. Okay. This, using Stirling approximation, we can write it in this form. These are all the things which are given in a standard textbook. I am not going into any of these derivations. Okay. So we can write that the change in free energy. Here I use the term delta F because Helmholtz free energy I use it, because EF is the formation energy, okay, and then TS is the configurational entropy term. There are two are there. One is SC is the configurational entropy, and ST is that around each vacant site which we have created, the thermal vibration, there will be a variation will come. So what is the contribution from the thermal vibration also has to be taken into consideration. Okay. We can substitute to SC the using Stirling approximation the value which we have got it, okay, for S, and if we do differentiate it and then try to find out the ratio of vacancy concentration to the number of atoms in the lattice, okay, then we will find that it's related to the energy of formation, okay, in an exponential term, and another is St by K, another exponential term comes into this picture, okay. In this, we assume that by some means we are able to measure the vacancy concentration at different temperatures. Then we can get information about the EF, okay, and also about that St by K. Okay. So this, so how will the plot look like? So if we plot log of the CV, the vacancy concentration, versus 1 by KT, 1 by T, okay, then this should be a straight line plot. The slope will give us EF by K, okay, we know the Boltzmann constant we can find out, okay. The point at which it cuts this y axis, this will give information about that St by K, right. So we can get both the information about the entropy term, thermal entropy term, as well as the formation energy which we can get it. Okay. Or if we know these values, then we can calculate theoretically what will be the concentration of the defects which will be produced in the material. What has been seen experimentally is that in most of the material close to melting point, the point defect concentration is of the order of close to around 10 to the power of -3 to 10 to the power of -4. It is within that range, which is what it has been observed. Okay. So here what I have done is that I have taken it from the literature, the value which has been determined experimentally for various pure elements. Okay. And here you can see that aluminium melts at the low temperature, tungsten melting point is high, correct? The lower the melting point, then we can talk about is the bond strength is going to be weak, correct? The higher the melting point, the bond strength will be high. This is reflected in the energy of formation also. So if you look at aluminium, it's around 0.6 to 0.77 eV is the formation energy, electron volt. Whereas in the case of tungsten, it is going to be like you can see that molybdenum, niobium, high melting elements, they have a higher formation energy, correct? But irrespective of this, at the melting point, the vacancy concentration is seen to be between 10 to the power of -3 to 10 to the power of -4 for most of these materials, correct? Okay. But what is essentially important is that This tells what is going to be the equilibrium concentration of the vacancies. Okay. One more thing which we have to consider it is that what do we mean by an equilibrium concentration of the vacancies? Okay. That is that concentration of the vacancy which brings about maximum reduction in free energy in the material. You understand that? That is, if I look at, try to plot, okay, the free energy change, that is, it comes like this, okay, with the number of vacancy concentration. So, at this particular point, when the vacancy concentration is going to be there, maximum reduction in free energy. But if the concentration of vacancy increases beyond that also, or less than that also, there is a reduction in free energy is going to take place. So, that system is stable, because free energy change there, but that is not the maximum. Okay. And up to this point, this is the critical concentration at which, by adding one more defect vacancy into that system, it goes into a free energy becomes high. Now, it will not be no more in thermal equilibrium, correct? In all other cases, yes, the defect concentration is there, but the defect concentration is bringing about a free energy reduction. This one should keep it in mind, okay? Now, if you have produced defects in the material at some particular temperature, okay, by whatever be the various means, will the defect always, this defect is going to move around, okay? Finally, what is going to be the concentration of defect in the sample depends upon how fast the defect moves. That is the migration energy part of it. What we will do it is that in the next class, we will talk about that, okay? We will stop it now.